let's put those derivative rules into practice, the ones for sine and cosine. We're going to save the more complicated ones for the later part of the lesson. But for right now, example 2, find the derivative of the following. Number 1, we've got y equals sine x divided by 2. Number 2, y equals x plus cosine x. All right, let's get started. So here's a question for you. Do I have to use the quotient rule on this first one here? Because I got sine x divided by 2. Well, not really, because that 2 is just a constant, and you could rewrite it as half times sine x, and then I can see that I'm just going to use a constant multiple rule. This constant of 1/2 is just going to go along for the ride. And I have y prime is equal to a half. What's the derivative of sine? Cosine. And it's done. Reet. Those two colors look smashing. Okay, number 2. Y equals x cosine x. I've got a sum of two functions. And the sum rule just says, hey, just take the derivative of each piece, add them together. Y prime is equal to, derivative of x is 1. The derivative of cosine is negative sine. And it's also done. Look how easy this is. Piece of cake. Yeah, and then you start the homework, right? Okay, anyway, let's look at example 3. Let f of x equal x squared times sine x, and we want to find the derivative of f prime of x. And notice that I've got a product here, x squared times sine x, so I'm going to have to use the product rule in order to find its derivative. Okay, I need to go back to purple. Okay, so f prime of x is equal to, this is twins dating twins, derivative of the first is 2x times sine x, plus the first one, x squared, times the derivative of the second one, cosine x. All right, and then, you know, if you wanted to, you could factor out, I don't know, I guess an x. So x times 2 sine x plus x cosine x. I'm not sure that made it any prettier, but there you go. Sometimes, you know, whenever you do the little factoring, it might turn into some sort of trig identity you can replace it with. Not too terribly frequently. Don't expect much of that on the AP Calculus exam because it's still supposed to be a calculus exam, not a trig exam. Okay, here's some graphs for this stuff. Let's take a look. All right, so here's the original graph in purple and the official color of the derivative graph right there in green. Okay, and let's do our little comparisons here. So notice that the derivative hits 0 right here, and then I follow that straight down, and you can see that there's a local minimum there. And then on this portion of the graph to the left of that 0, it's negative, which means our slopes should be going downwards, and it is, and then it transitions to going upwards. And then what the heck's happening right here? Well, right here the derivative is 0. And just because the derivative was 0, like it was right here, you didn't have a minimum or a maximum point. Instead, this one's called a point of inflection right there. And we'll talk more about those things in another chapter, in another module. All right, and then we've got positive slopes some more until we hit this point here, which is our maximum point, and then negative slopes going downwards. All right, I think we got one more of these things. We've got given y equals e to the x sine x cosine x, find dy dx. What? I've got 3 functions. How are you supposed to take the derivative of 3 functions? Using the product rule, now it's triplets dating triplets. You got, remember, if you keep it in the same order, you first take the derivative of the first one, then the second one, and then the third one, and then you keep the other 2 exactly the same. It looks scary, but it won't be. All right, let's look here. So dy dx, that just means y prime, but it's the Leibniz notation here. So dy dx is equal to, so we're going to start off with the derivative of the first one here. So the derivative of e to the x is just e to the x, and then sine x cosine x. All right, and then we're going to take, here, let me erase that one. Now we're going to take the derivative of sine x, but the other 2 are going to stay the same. Plus e to the x, derivative of sine x is cosine x, times another cosine x. Right? And then plus, Now we're going to keep two of them the same and only take the derivative of cosine x. E to the x sine x, and the derivative of cosine x is a negative sine x. Oops. All right, and then maybe I just clean this up just a little bit. E to the x sine x cosine x plus e to the x. That, of course, will be cosine squared x. And then e to the x. Whoa, that's not a plus. This one's going to be a minus sine squared x. Is there anything else I can do with it? And I'm just doing the algebra on this just because what if this was a multiple choice question and I just have to match up my answer with theirs? And I just have to just do some transformations till I get there. Maybe I factor out an e to the x, and then I have sine x cosine x plus cosine squared x, and then minus sine squared x. And then maybe there's some sort of identity that we could use here. Like, for example, I have sines and cosines which are squared, and that Pythagorean identity is sine squared plus cosine squared is equal to 1. Maybe I should throw some x's in there, okay? That's not quite what I have, so maybe what I do is I can solve this thing for cosine x and maybe substitute it in my equation, get rid of the cosine squared, or vice versa. Maybe I solve it for sine squared so that I can substitute the sine squared out and get rid of it. It just totally depends on what it is that I'm, trying to aim for. All right, let's take a look at the graphs for these as we conclude this. So here's the graph of the original function. That's pretty interesting looking. And then in green, we'll take a look at the derivative there. And the same kind of relationships hold true where we have the derivative equal to 0. We have like a horizontal tangent line right there. Same thing here and here and there and down here. All right, and then just one last time. Here is, are you kidding me? That's okay. Here, welcome back. Let's go right back where you left off. This is the derivative of a product of three functions as we saw before, right? And that's exactly what we applied on that last problem.